Okay, so we have reached the last part for chapter 4. So chapter 4's last part is power. Power is defined as the rate of work done. So whenever we have the word rate, rate means over time. Over time. So if it's saying the rate of work done, it means work done. Okay, work over time. If it's saying the rate of drinking, so it's drinking over time. Alright, so rate just means over time. Okay, so here the power is defined as the rate of work done, which means work done is over time. So work done is in joules, time is in seconds. So the unit for power is joules per second or watt. Capital W. Watt. Okay. So when you write watt, you use the capital W. Or joules per second is also fine. Other common units is horsepower, 1 HP, 746 watt. We won't be using this in our syllabus because this is just for your general knowledge. All right. Okay, so that is power, and power is also defined as the rate of energy change. Okay, so what is energy change? Energy change is delta E. Remember that we learned that W, or work done, should be equal to the change in KE. We had our work energy theorem. We also learned that work done happens when we have the change in gravitational potential energy. Similarly, change in elastic force. All these are delta E, the change in energy. So work done is also called the change in energy. And if we are talking about the rate of energy change, which means it's delta E over T, which is also the same as work done over T. Alright? So going to our example. A block of weight 120 newtons. So we have weight, okay, is 120 newton. Moving downwards along a plane incline. So it's moving downwards. Okay. And the angle is 30 degrees with the horizontal at a constant speed of 10 meters per second in 3 seconds. So the U equals to the V equals to 10 meters per second. The time taken is 3 seconds. The work done per second. So it's asking what is work done over time in overcoming friction. So the work that we are interested in is work done by friction. Work by friction, right? So this is work by friction over T. What is it? Right. Okay, so to find out what is the work done by friction, we obviously need to draw our free body diagram and also need to know what is the distance traveled in 3 seconds, right? So to find out the distance traveled in 3 seconds, we use by the kinematic equation, we have S equals to UT plus 1 over 2 AT squared. There's no acceleration here because our U equals to V. So there is a 0 acceleration. This leaves us with S equals to UT. So U is 10. T is 3. So this gives me 30 meters in distance. Okay. So now I have to find out what is my friction force. So I have reaction force, which is always perpendicular to the surface. I also have weight, 120 newtons. And this is my angle here. So this is 120 cosine 30. And this is 120 sine 30. Okay. And then I also have friction. Okay. So since we are not given the coefficient of friction, we need to solve friction in terms of using this equation, which is Fx equals to 0. This is our x. Okay. Kejap, nak kemaskanlah kejap. Okay, we need to solve for friction. So Fx equals to 0. And in my axis, I have minus F plus 120 sine 30, right? So my friction is 120 times sine 30. That is my friction. Okay, so the work done per second in overcoming friction is, so the work done for friction is it's friction, right? Friction force dot product with S, and we already know the parallel component to friction is our distance that we calculated, which is 30. So let's just times it with 30. Okay, so this is work done, so this becomes 120 sine 30 times 30, and the answer is, okay, so the answer is 1800 joules for 3 seconds, because this was the work done that we achieved in 3 seconds. Remember, we calculated the distance for 3 seconds, and this refers to the work done that we achieved in 3 seconds. So now the question is asking you, what is the work done per second? So work done by the friction for 1 second. For 1 second is 1800 joules divided by 3, and the answer is 600 joules per second, or 600 watt. This guy is a second. Okay, on to our next question. How much power is delivered to a turbine below a dam of height 50 meters? So turbine is the rotating thing, right? So it's below a dam, so water falls on the turbine. It's water, okay, of a height 50 meters. So there's a height here, that is your height, equals to 50 meters, that delivers 1 meter cube of water in 1 minute. So time is 1 minute or 60 seconds. And height is 50 meters, and it delivers 1 meter cube of water per minute. Okay, so how much power is delivered? Power equation is work done over time, and work done is the change in energy over time. What is the change in energy that we can observe happening when the water falls from a height? mgh, right? Ug equals to mgh. Now, how do we get the delta E? This is E. How do we get the delta E? We know that the water starts from here to here, so there is a change in height. So we have a change in E. When we have a change in E, we have work done. So this becomes mg h1, H initial minus H final. So H final minus H initial is your delta E. Alright, so assuming that here is ground 0 and here is 50, because it is falling at a height of 50, right? Now the next step is to find out what is the mass of water that falls in 1 minute. So mass is in kg, right? So we have R, which is 1000 kilogram per meter cube. We just want the kg, so we are going to times it with 1 meter cube. Okay, so this is the mass, and it is 1000 kilograms. Okay, so now back to our equation here. Let me just get rid of this first. That is 1000 kilogram. So now my P equals to W over T, or change in energy over T. The change in energy is M, which is 1000 kilogram. G is 9.81, and our delta H is 50, right? and time is 1 minute. 1 minute is 60 seconds. So the answer to that is 0.49, sorry, that is 8.175 times 10 to the 3 watt. Okay, so now you're gonna ask me, Doktor, kenapa power dia positif sedangkan our work done was a negative? Because we are losing energy as we are falling down. Our delta H is a negative, kan? If our delta H is a negative, shouldn't our delta U be a negative? And then shouldn't our work be a negative? And shouldn't our power be a negative? Betul, you are correct. But now it's asking how much power is delivered to a turbine. It's not asking what is the power lost by the water. It's asking what is the power transferred from the water to the turbine, which means that the turbine is increasing in energy, right? So water loses energy, right, when it falls down because it's losing H. But that is taken by the turbine, and the turbine increases in energy. So that means it's a positive work. This guy is negative work. But I am calculating for the power delivered to the turbine. So which is why I ignored the negative sign, because I already knew that the turbine will have an increase in energy, will have a positive work done, and will have positive power. Okay, so that's your explanation on why I ignored the negative sign in this equation. Because I am not calculating the work done the energy lost by the water, but I am calculating for the energy gain by the turbine. Remember, energy gain equals to positive work. Alright, so that's it from me. I'll see you in class soon. Bye-bye.